Hello, class. Hello and good morning. This is going to be my presentation for our last homework set. I'm going to do two exercises because, as we're going to see, these are going to be mostly visual problems, so I think I'll be able to get through them fairly quickly. We're going to do 13.9 and 13.10. Okay, so let's see what we got. Okay, so 13.9 asks us to determine if the flow map here, which is defined, in two-dimensional space, is topologically transitive. So more or less, the definition we're given for topologically transitive is if we have some flow map and we initialize it at some, point in the space, then eventually, over time, that map will take our initialized point to every other point in the space. I've only shown the path of one particular point here, so it may not be the most convincing argument, but we can sort of get an intuition for, because cosine and sine are at different periods here, they're going to be out of phase. And so we're going to continually get this chaotic motion that it just like sweeps out all of space, kind of traces out all of space as the magnitude increases, as t increases. So I tried my best to write that up here, that, I think I missed a closing bracket here, but that, the flow map takes X to a little ball around any little vector, around any vector in the space, eventually. So I also tried to make a little Desmos calculator that shows that. I'll see if I can pull that up. Hopefully this shows up on the video, but I will just run this example for a couple points in time. So we see that as time increases, the points spread out and they appear to trace out all of space. I can kind of move forward in time so we can see that a little bit more clearly. Okay, and then it starts to get a little bit crazy after a while. So all right, well, and moving on, hopefully that was convincing. We can move on to the next flow map. So this one, we see that the cosine and sine are in the same phase, so we'll get a different type of motion here. This little red dot is actually a circle in the 2D plane, and what we'll see is that phi takes pretty much, you can always find some point in the space where no matter what point you act phi upon, that point will never be sent to your little region in R2. So tried to make that's what it says here. For no time t will phi of x be within some given region. You can choose that given region with tolerance of some small epsilon. See if I can pull that graph up here. Okay, and then I'll just try to zoom in. We'll watch as t increases a little bit. Okay, so we see the points spread out over time, and eventually I could pick a small region in space, with some small radius, that these points, no matter how far you let time move forward, will never fall into that region of space. Okay. All right, and so moving on to the last question, 10.13. This one was a pretty interesting question. We're given a recursive sequence defined on the open half interval 0 to 1 as, well, I won't read this all out, but more or less, if x is between 0 and 1/2, you double the previous x to find the next x in the term in the sequence. If the previous x happens to be between 1/2 and 1, then you'll double it and subtract 1. Okay, so then we construct a flow map using this recursive sequence. Just a bunch of signs with integer period lengths. Okay, and so here's a given given plot for the flow map for just some, small initialized x here on the y-axis, just showing how that evolves over time. It appears to me that the dynamics do exhibit mixing. Main reason that makes me say that is because as long as I wait long enough, it looks like any starting x will be sent to every other point in the space, just the region between 0 to 1, as long as you let t go on long enough. Tried to make a little calculator to show that. Hopefully these are showing up on the video. If not, I may have to remake this video. Be a good time. Okay, so, technicalities aside. Oh, maybe it's not working. Oh no. Oh, here it is. So I'm just changing the input value, smoothly, slowly over time. You can see it creep up here on the y-axis, but it does look like, as phi takes that initialized point and sends it to pretty much every other point in the space here between 0 and 1. It's kind of a fun graph to watch. Okay, and we also, just because Desmos doesn't allow me to make recursive definitions very easily, I ran this again in Wolfram, in the Wolfram cloud, initialized for like 5 or 6 points here, kind of between 0 and I think 0 and 0.1 or something like that. But again, we can see pretty much it does seem to exhibit mixing, as pretty much every point in the space is traced out by whichever point you initialize phi at. It's pretty interesting. A lot of cool graphs or pictures, cool colors going on. Okay, so yeah, these dynamics do seem to exhibit mixing. Phi of x will eventually travel to all the points in the open half interval. Especially, that was looking at just truncations of this recursive sequence. If you let if you let this definition go all the way out to infinity, I'm sure that you get some more erratic behavior. All right, and so that's pretty much all I have for you guys today. I hope that was insightful in some way, and you guys have a lovely class today. Have a good summer, and I'll see you guys tomorrow.